So anyway, let's go over first law and its applications quickly. So the statement of the first law, that net heat supplied during a thermodynamic process is equal to the change in internal energy plus work done by the gas. The only thing you have to be careful in this statement in physics is that W is work done by the gas. Whereas the way you write the statement in chemistry, okay, because you define it as work done on the gas rather than work done by the gas, you can write an alternate version of this, that Q plus W is equal to delta U, but I'll just write this as W prime. So W prime is work done on the gas. So there's a difference between the two. Work done on the gas during a process becomes minus of integration PdV. Okay, so here we are talking about work done by the gas, so we have to be careful about that. So this is the what we call the state. This is what we call the path function. Okay, because it is the area under the P versus V graph. Okay, so it is a path dependent quantity or a path function. Then U of course is internal energy. And from kinetic theory of gases, we have understood that internal energy is the total kinetic energy of gas molecules. Okay, so these are things that you're familiar with. I'm just doing a quick recap. So it is number of moles into number of degrees of freedom into 1 by 2 RT. Okay. So that is why we can define in any thermodynamic process, we can define the change in internal energy delta U as NF by 2R delta T. And as you can see, it depends on only one parameter changing, which is the temperature. So this becomes what we call a state function or path independent function. Okay. Whereas Q, which is the sum of these two, Q therefore becomes, this is the net heat supplied to the gas during the process. And this becomes what we call again a path function. So this was the statement of the first law of thermodynamics, which you are all familiar from chemistry also. But just remember, in chemistry, the work done is defined on the left hand side as the work done on the gas. So it is minus integration PdV. Whereas here we define W as work done by the gas. So it is on the right hand side and it is integration PdV. So in this case, when the gas expands, the work done by the gas is positive. Okay, so keep in mind that expansion of the gas means that the work done by the gas is positive. Compression of the gas means that the work done by the gas is negative. Whereas in the case of when you define it as work done on the gas, in this case, when we compress the gas, the work done on the gas is negative. And when we allow the gas to expand, then the work done on the gas becomes, sorry, it's the other way around. In the case of expansion, the work done on the gas becomes negative. In the case of compression, the work done on the gas becomes positive. So this is one small point to keep in mind. Okay. And then of course we had seen the applications for the 4 standard type of processes. So I'll just quickly take you through them. So isochoric. So that on the PV graph looks like a vertical line. Okay, so volume is constant. So work done is 0. Okay. So Q is equal to delta U is equal to NF by 2R delta T. So Q is defined as NCV delta T. That is CV, which is the isochoric molar specific heat capacity, is therefore defined as F by 2R. And obviously you know that F is 3 for monoatomic gases and it is 5 for diatomic gases. And the second process we had seen was isobaric. Okay. If anybody has a doubt, please ask me, because I'm assuming that these are things that you are very familiar with from chemistry. So we are going to focus more on the applications today, but I'm just taking a quick recap of the formulae for the benefit of Some of you might have missed lectures or might not have seen this carefully. Okay. So isobaric process is defined where one is defined as one in which the pressure is constant. Okay. So that looks like a horizontal line. Okay. So if the volume is increasing while the pressure is constant, we say it's isobaric expansion, and vice versa. So the work done, which is integration P dV, becomes P delta V. Okay. And from ideal gas equation, we can also say it is nR delta T, because when pressure is constant, if pressure is constant, then we can say P dV is equal to nR dt. So P delta V is equal to nR delta T. But this is specific for isobaric, right? Then delta U is obviously nF by 2R delta T. This is the same always because this is a state function. Okay, so that's the same formula as what we have over here for the state function. So Q, which becomes delta U plus W, in this case Q becomes nF by 2R delta T plus nR delta T. Okay. And we define the Q as NCP delta T. So from that we get the relation that isobaric molar specific heat capacity is given by F by 2 plus 1 into R, or Cp is equal to Cv plus R for any ideal gas. So this becomes a very easy formula to understand from just these two processes itself. If there's any confusion or doubt in any of these steps, please let me know. I will explain again. Yeah, just a minute.
Hello, sir.
Yeah, Jagannath, what was your question? I didn't ask. I didn't get it. Sorry. And Shikhar, what is your question, Rita? Achha, this one, na state function. Okay. Yeah, this I've written it as this is a state function. Delta U is a state function. So that is why it has a common formula for all the different type of processes. Is it clear, Rita? Yeah, Shikhar, what is your question, Rita? Okay, no problem. But what is your question then, Rita? How did we prove T delta V is? We proved that like this, that for in general for an ideal gas now, we have the equation of state for an ideal gas, that PV is equal to nRT. Okay, so if we differentiate both sides now, we'll get in general first function into derivative of second plus first function's derivative into second function. And this is the product rule. So that should be equal to nr into dt, because n is constant, r is a constant, but p, v, and t in general are variables. Understanding? No? So we are using the product rule in differentiation. If a function is the product of two other functions, no? Then f prime becomes u v prime plus u prime v. So basically what we say that df by dx is u into dv by dx plus du by dx into dv. So in other words, we can say that the small change in the function is u into dv plus du into v. This clear na? Yeah, Shikhar, this part is clear na? Okay, so that is what we apply over here for this statement. Okay, yeah, got it. So this is the general relation. This is the general ideal gas equation. Okay, in you can say differential form. This is in differential equation form, whereas this is the original form of the ideal gas equation. Okay. Yeah, Jagannath, I'll take you back just a moment. Okay, I understood. So in general, when we write that ideal gas equation in differential equation form, we get this relation here. Okay? So now in this relation, when we specifically apply the condition for isobaric process, for example, so P is constant, so dP becomes 0. So then for isobaric process, P dV is equal to nR dt. Okay, so therefore work done, which is integration P dV, can be written as P into integration dV. It can also be written as nR into integration dt. So P delta V is equal to nR delta T, which is equal to work done. But similarly, if I talk about isochoric process, okay, then for that I have a different relation. Their volume is constant, so dV is 0. So I'll have the relation that dP into V is equal to nR dt. So first of all, for this process, the work done will become 0, because integration P dV will be integration of 0. But secondly, integration of dP into V is equal to integration of nR dt. Here the volume is constant, so we'll have V into delta P is equal to nR into delta. So for example, isochoric process has this property that volume into difference in pressure is equal to nR into difference in temperature. Whereas isobaric process has this property that pressure into difference in volume is equal to nR into difference in temperature. Okay. Or here we can say that volume is proportional to temperature because pressure is constant. Here we'll say pressure is proportional to temperature because volume is constant. So all these things are interconnected. So anyhow, it's a subset of this thing, how we get the work done is equal to nR delta T. Secret that you have understood. Okay. Yeah, Jagannath, I'm just taking you to the previous section. So just let me know what is your doubt in this. You can unmute yourself and ask the question directly also, if your microphone is working. After the curly bracket, this part here, this or this. The first para, okay. So this is also state function. delta U is a state function. That okay. Okay, so people will move on. This is clear now. Isobaric and isochoric. Okay, I'll stay for some time. But this is part of the notes of the previous. I'm just doing a quick recap. Two standard processes we had done last time. Okay, so I'm just moving on to the next section now. Make sure you just understood this. If there's any doubt, ask me, because otherwise it's there in your notes for the previous lecture. Now the next two processes were isothermal and adiabatic. So isothermal is one where temperature is constant. So if temperature is constant, it means internal energy is constant, or delta U is zero, because delta U equal to NF by 2R delta T will be zero, because there's no change in temperature. So basically we are not allowing the temperature of the gas to change. That means whatever heat is supplied to the gas is either converted into mechanical work, or we do work on the gas and extract heat from it. Okay, so Q is positive, W is positive, means heat supplied is converted to work done by the gas. That is the case of the isothermal expansion. Now, on the other hand, if Q is negative, so work done is also negative. That means work is done on the gas, okay, and heat is extracted from it. Okay. So that is the significance of this. Now P becomes inversely proportional to V, because this is constant. Okay. So the isothermal process in a PV graph looks like a hyperbolic kind of curve. Okay. So this is what we call an isotherm. P is inversely proportional to V. One thing you might want to note down here is that if you compare two different isotherms like this, T2 is greater than T1. The greater the temperature, the further away the isotherm is from the origin. Okay. This is a comparison of different isotherms, or isotherms at different temperatures for a given sample of gas. So, because you can see that P is equal to some constant, which is nRT divided by V. So the larger that constant, the further away it is from the origin, that hyperbolic curve. So this is a good way to visualize the PV space, that the PV space is actually like every point has a value of pressure, volume, and temperature, because it's lying on some or the other isotherm. Okay. So any point on the PV space is not only lying on a particular isobar and an isocore, so it has a particular pressure and volume, but it's also lying on a particular isotherm, so it has a particular temperature. So hope this point is clear to all of you. Right, now the next thing, the calculation of work done. So work done is area under the graph. So if we are, for example, going from a volume of V1 to a volume of V2, case of this isothermal expansion, so the work done will be this. It is nRT integration dV by V from V1 to V2. So it is nRT ln V2 by V1, which you can notice is a positive quantity because V2 is greater than V1. Whereas if we are talking about a compression, then the work done by the gas would be a negative quantity. Okay, so Q is equal to W is equal to nRT ln V2 by V1. Now, likewise, if we had a situation where we are going from a higher volume to a lower volume through an isothermal process only, the formula would be the same. So suppose this point has volume VA and this point has volume VB, but we are going from A to B this time. So in the case of A to B, volume at B is lesser than volume at A. So we are going through an isothermal compression. So here we'd see W is equal to, so by the same steps, W would come out to be nRT ln VB by VA. But here since VB is less than VA, so the work done comes out to be a negative quantity. Okay, because ln x is positive for x greater than 1, ln x is negative for x less than 1, ln x is equal to 0 for x equal to 1. So just keeping that in mind. And ln cannot be defined for negative terms. Of course, that doesn't make sense here because the ratio of two volumes cannot be a negative quantity. It is a positive quantity. The question is whether it is greater than 1 or less than 1 or equal to 1. So again, in this process also, Q is equal to W equal to nRT ln VB by VA. But that will be a negative quantity over here because we're talking about an isothermal compression. Whereas here that would be a positive quantity because we are talking about an isothermal expansion. So just something very simple to keep in mind. Okay, so any doubts with this part? Anyone? Okay, now let's come to the fourth and final of the standard processes. That is called the adiabatic process. Yes. So Shikhar, remember Q is heat, net heat supplied to the gas. Okay. And W is work done by the gas. So for an isothermal process, if Q is equal to W is equal to a positive quantity, that means heat is supplied by some external agent to the gas. Okay. And work is done by the gas. because it expands, and vice versa for isothermal compression. Okay, Jagannath. Okay, just go through this. You don't need to write this down or anything because it's there in your notes from last time. Just make sure that you remember these points because we'll be using that in solving questions. Okay, Jagannath. So I hope these 2 points are clear to you. Isothermal expansion Q and W, they are positive quantities. Q equal to W is a positive quantity, whereas isothermal compression Q equal to W is a negative quantity. Okay. So the fourth and final. Okay, good. Fourth and final of the standard processes. Yeah, no problem, Jagannath. It's okay. Is the adiabatic process. So by definition, you know this is one where there is no heat exchange. So neither we are supplying heat to the gas, nor we are extracting heat from the gas. Q is simply equal to 0. So for this process, delta U plus W is equal to 0. So W becomes minus of delta U, that is minus NF by 2R delta T, because delta U obviously is the state function, which is delta state function. So these are the formulae, that Q is 0, delta U is the standard formula, and in this particular case, work done becomes adiabatic work done becomes like this. Okay. So you can see that either W is positive, so delta U is negative. That means work is done by the gas and its internal energy reduces. Okay, so that is the case of adiabatic expansion. Okay. Or the simple inverse of this, the vice versa. Okay. Or W is negative, so Q is positive, because Q is negative of delta U. So, sorry, not Q, delta U. Okay. So this is the case where work is done on the gas. That's why work done by the gas is negative, and its internal energy increases because delta U is positive. So this is the case of adiabatic compression. Okay. Now one more point we should understand over here, that since Q is 0, okay, but delta T is non-zero, the temperature is changing. Therefore, molar specific heat capacity is 0. Okay. Molar specific heat capacity for adiabatic process, that is equal to 0. So C is simply defined as, Q upon M upon n delta t, number of moles into delta t. So here what is happening, Q is 0, but delta t is non-zero. So that means C must be 0. Now the other thing that we learned about adiabatic process is the equation of the curve. It is called the equation of the adiabat, or adiabatic curve for a PV graph. That thing. Okay. So there we had seen that PV to the power gamma is constant. Or if we compare any 2 points on an adiabatic curve, where gamma is the ratio of Cp by Cv, or it's related to degrees of freedom like this. So on the PV space, now today we'll look at this in a little bit more detail, the adiabatic curve. We'll understand that an adiabatic curve looks hyperbolic in nature only, but it's a different hyperbola compared to the isothermal curve. If this is the one where P is proportional to 1 by V to the power gamma, then compared to an isotherm, it's like this. Isotherms will be like this. So during an isotherm, adiabatic curves have sharper slope. Yeah. Okay, because you can also understand one thing, that if you're going from this point to, let's say, this point, E to B, it is an adiabatic expansion. Okay. So the temperature should decrease. Okay. Whereas if I go from B to A, it's an adiabatic compression. So the temperature will tend to increase. So that is why you can see that this isotherm, suppose, is at T1. This isotherm is at T2. You can see T1 is greater than T2. So the direction of the adiabatic curve is always such, or the slope of the adiabatic curve is always such, that expansion results in cooling and compression results in heating, something that we just saw above. So always remember, in an adiabatic process, expansion, it results in cooling. Okay, because internal energy decreases. So delta T is negative. And compression, it results in heating, because delta T will be positive because internal energy is increasing. So that same thing you can see in the graph now. If you're going in such a direction along the adiabat that your volume is increasing, so an expansion is taking place, so it results in cooling. Whereas if you're going in the opposite direction from B to A, where your volume is compressing, it will result in heating up of the gas. Now I won't get into the derivation of this equation again, but just briefly I'll tell you how we did it. We used PV equal to nRT equation in differential form. PdV plus VdP is equal to nRdt. So that was one equation that we used. Okay. And we use Q is equal to delta U plus W, but in this case Q is 0. So delta U plus W is 0. But again we use this in differential form. Du plus dW is 0, which means that nf by 2 r dt plus pdv must be 0. Okay. So solving these two equations, we get the relation between PdV and VdP, and that is that. Okay, PdV is equal to minus of VdP into Cp by Cv, or like this. This one. So you get from these two equations, we get this, and from that we get the fact that PV to the power gamma is constant. Okay. So I've done this derivation in the previous lecture. You can go through that section. But the derivation is not really important for us. The final result is the more important thing. Okay. So let us do a quick numerical problem. Okay. So a sample of helium gas at pressure 1 atmosphere, volume 2 liters, and temperature 100 Kelvin is first expanded, is first compressed adiabatically to a volume of 0.25 liters, some pressure and some temperature, and then it is isochorically cooled down to original temperature. So T3 equal to T1 equal to 100 Kelvin, some pressure P3, some volume V3. Okay. So first of all, plot the series of two processes in a PV diagram and find all the unknown quantities P2, T2, P3, V3, all these things. Okay. And secondly, find Q, delta U, and W for first of all the adiabatic compression, and then the isochoric cooling. Okay. So yeah, Jagannath, I'll take you back to the previous slide also. Don't worry. But first, people just note down the data of this question and try this out. Okay. You have done these type of questions in chemistry, so it should be quite easy for you. You just treat this like additional practice. Okay. You've done these processes in chemistry also, no? Yeah. Yeah. So it should be pretty easy, no? Just try to work it out quickly. Start with the graph. I'll make it for you soon. But keep in mind what I told you about graphs earlier, that you can visualize the PV space as if it has isotherms cutting through it. Now, those rectangular hyperbolas are a series of isotherms at different temperatures, and you know how the adiabatic curve looks compared to that. You know how the isochoric line looks compared to that. You know how the isobars look compared to that. So it's easy to visualize like that. Okay, just try to plot the graph and come up with the answers for these things first. Okay, and also use the standard value that one atmosphere, take the approximate value of 10 raised by 5 pascals. And of course, you know that 1 liter is exactly equal to 10 raised by minus 3 meter cube. So therefore, 1 liter atmosphere becomes 10 raised by 2 joules. So this conversion, the more exact value actually is 1.01 into 10 raised by 5. But here we'll use the approximate value. Yeah, Jagannath, I'll just go back to the earlier part once. But once again, just go through it and let me know if there's any doubt, because it's there in your previous notes. Okay. Okay, so okay, we'll come back to the question, Jagannath. Okay, okay. Okay. So I'm now sort of making a rough graph, and I'll come to the calculation after completing the graph. I'll approach the understanding of the question more by the graphical method first. So pressure in atmospheres, volume in liters. Okay. And we're talking about a sample of helium gas. So its degrees of freedom is 3. It's monoatomic gas, so gamma is 5 by 3. So in this, if I undergo an adiabatic compression, that process is, let's say, like this. So this volume was 2 liters. This pressure was 1 atmosphere. Now this volume is reducing to 0.25 liters. So this we have to find out. Okay. And also we know that the value of temperature at this point, let's just call this E so that we don't create confusion. This temperature was 100 Kelvin. So we can see that PAVA to the power gamma will be equal to PBVB to the power gamma. So pressure at the point B will become this. Okay. So it will be 1 atmosphere into 2 by 0.25 to the power 5 by 3. Okay, so that will be 2 to the power 5. So that's how much? 32. So 32 atmospheres will become the pressure at the point. So at the end of our at the end of our expansion, adiabatic compression is what will happen. Okay. Now also you can see that the isotherm at the point B, if I do an isotherm, it's like this. And at the point A, I draw an isotherm, it's like this. So these are isotherms, let's say, at T2 equal to something I want to find out. This is at T1 equal to something. Okay. So my second process should look like this. It should bring me back from B to the original isotherm, which is at the temperature T1 equal to 100 Kelvin. So that is what the graph of the second process should look like. Okay. So now once I know this pressure, I also know that PA upon TA is equal to PB upon TB. Okay. So 1 atmosphere into 2 liters divided by 100 Kelvin is equal to 32 atmospheres into 0.25 liters divided by the new temperature. So temperature at the point B should become become 400 Kelvin. Or you can also use the relation for adiabatic compression. PV to the power gamma is constant. That means so T into V to the power gamma minus 1 is constant. So we can say that TA VA to the power 2 by 3 is equal to TB VB to the power 2 by 3. So temperature at B will be so that's another way we can do this. So that is the state at the point B, pressure, volume, and temperature. Okay, so now for the process AB, before we come to BC, let's also do the calculations of the first law of thermodynamics. No, Shikhar, we can't use that na, because it's not an isobaric process. Na? NCP delta T हम कब use करते हैं ना? Only when it is isobaric. Na? This is adiabatic process. So additionally, for A to B, which is the adiabatic compression, the formula we'll use is this, that Q is 0 by definition and W is equal to negative of delta U. Okay. So delta U is NF by 2R delta T. So that is N3 by 2R into T2 minus T1. So we can write that as 3 by 2 into P2 V2 minus P1 V1 using the equation of state. Okay. So internal energy will increase, as you can see. So P2 V2 is how much? It is 32 liters into 0.25, sorry, 32 atmospheres into 0.25 liters minus P1 V1, which was 1 into 2. But this will get multiplied with 10 raised power 2 when we convert this to joules. So this is becoming 8 minus 2, so that's 6. 6 into 3 by 2, so that will become 9. So 900. So delta U will be plus 900 joules. So as you can see in the graph, the temperature is rising. It's an it's an adiabatic compression. So the temperature is rising. So the internal energy has to decrease, has to increase. Shikhar, the formula that delta U is universal because delta U is a state function. So this formula this is universal because delta U is what kind of quantity? It is a state function. Okay, but the other formulae that Q is 0, so W is minus of delta U, those are specific to adiabatic. Like that for isobaric, Q is NCP delta T. For isothermal, Q is not defined in that way. Q is defined as W, that is nRT log of final by initial. For isochoric, it becomes NCB delta T. So that is the same thing as delta U. So the path function quantities Q and W, their formula is different for the different processes. Whereas the single state function delta U, that has a universal formula. Okay, Shikhar, hope the point is clear, beta. Okay, very good. Yeah, Jagannath, I'm waiting, don't worry. Just write down up to this delta U. So W will be minus 900 joules and Q is 0. So the adiabatic compression is completely solved now. We've got the thermodynamics part also. We've got the equation of state part also. So if you finish doing this part, then try out the second part, the B to C isochoric cooling till it's coming back to the temperature of 100 Kelvin. Yeah, people, I'm waiting for the answers for the second part. Those who have finished this first part of the question, you have to tell me the pressure and volume and temperature in the final state C, and also Q, delta U, and W for that process BC, which is our isochoric cooling. Yeah, W is 0, very good. Q will be equal to delta U will be equal to minus 450 क्यों है बेटा? He's coming back to the same temperature, no? So the delta U should be, see, between AB and BC, you are working between the same two isotherms, no? So the temperature difference is the same. So जितना internal energy A to B में increase हुआ है, that much only should decrease in B to C. Even though C is not the same point as A, but the internal energy at C is the same as at A. You understanding, Devansh? So just check your calculation once. And yeah, Samar, the pressure value is correct. Good. Yeah, I'll just tell you, Jagannath. Below 400 Kelvin. Okay. This part, okay, P2 is 32 atmospheres, V2 is 0.25 liters, and the temperature is 400 Kelvin. This is at the point B. The state of the gas at the point B, P2, V2, T2. They are 32 atmospheres, 0.25 liters, and 400 Kelvin respectively. So that is at B, beta. At the point B. This one, no? It is at the point B. This is the state of the gas at the point B in my graph. Yeah, Samarth, you given the answer in liter atmosphere. You have to just convert it to joules. Rest it is correct. हाँ बेटा वो मैंने ऊपर लिखा था ना समर. This relation. This is how we convert from liter atmosphere to joules. Yes, Shikhar, that is correct. Good. Devansh, what is the pressure and state that you are getting for the point C? Yeah, Devansh, did you get the delta U as minus 900? Okay, good, Devansh.
Yes, yes, good.
Okay, good. And Samarth, you understood ना कैसे उसको convert करना है from liter atmosphere to joules? Okay, good. Okay, so let's concentrate on the second process now. So the second process is the isochoric process. So we are at temperature of 400 Kelvin, pressure of 32 atmospheres, and volume of 0.25 liters. From there we are coming isochorically to to the point where the important thing is that the temperature is equal to 100 Kelvin. So now we want to find the pressure, and obviously the volume will be the same because it's isochloric. So pressure is proportional to temperature in isochloric process. Okay. So P3 by P2 should be equal to T3 by T2. So this should be equal to 100 by 400. So that's how we are getting that the pressure should become 8 atmospheres. So now we know that at the point C, the pressure is 8 atmospheres. The volume is obviously the same volume, 0.25 liters. And the temperature was given to us in the question is back to T1, which is 400, sorry, which is 100 Kelvin. Yes, that's correct, Shikhar. But that's in liter atmosphere. So now then the other thing is because it is isochoric process, it is isochoric cooling B to C. Q will be equal to delta U, which will be a negative quantity. You will extract heat from the gas and W will be 0. So basically heat is extracted and internal energy reduces. Logically, that is what is happening in an isochoric cooling. So Q equal to delta U is Nf by 2R delta T. So that we can write as 3 by 2 into 8 atmospheres into 0.25 liters minus 32 atmospheres into 0.25 liters. Okay. So remember in an isochoric process, we also have this that NR delta T is delta P into P. Okay. So NR delta T here is the difference in pressure 8 minus 32 into the volume 0.25 into 10 raised power 2 joules. So you see that this becomes minus 900 joules. Or B to C. Work done is 0 and Q is equal to delta U equal to this much. Yeah, Shikhar, it's almost 9 minus 909. That's correct actually. But I'm just taking 1 atmosphere as the approximate value of 10 raised per 5 pascals. So that's why I'm getting 1 liter atmosphere. I'm taking the approximate value of 10 raised per 2 joules. Okay, so these are a couple of examples of the standard type of processes where you have to use the formula of the standard processes. Yeah, that's correct. That is a more correct value actually. The one value of 1 atmosphere is 1.01 into 10 raised power 5 pascals. So the more correct value of this is 101 joules. Okay, so this is as far as the standard processes is concerned. Now we can also have a situation where we want to apply first law of thermodynamics in a non-standard process. So that was what was asked in the question actually. We had to make the graph in the question. Often the questions are graph based, like you have to select the correct graph in a JEE paper. So that's why you should know how to visualize this in terms of graph. Okay. So that was part of the question, plot the series of two processes in PV diagram. That's why I made the graph. In JEE, it will come like you have to select the graph, which is the correct graph. Like that. Okay, Jagannath, finished. This is what we wanted to check out, the graph again, or yeah, Shikhar, to be able to understand the graphical representation of one thing you should do is when you are studying about the four standard processes, isothermal, adiabatic, isobaric, and isochoric, make sure that along with the formula you are very clear about the graph of the processes. And secondly, like I explained today, that think of the PV graph as actually a three-dimensional graph, because every point is not only having a particular pressure and volume, but every point is also lying on a particular isotherm. So that will help you in visualizing the graphs. Okay. So just think of any point in the PV space, in a PV graph, any particular point, it lies on a particular isobar. So it has a particular pressure, let's say P1. It lies on a particular vertical line, which is an isochore. So it has a particular volume. But it also lies on a particular isotherm. So it has a particular temperature. So every point has three coordinates: pressure, volume, and temperature. So any process you can understand on the basis, and you can visualize that your isotherms, when you go away from the origin, the temperature is increasing. So this is T1 minus delta T, whereas this isotherm will be at some T1 plus delta T. So this visualizing the PV space in terms of not only the pressure and volume coordinates, but also the isotherms and therefore the temperature coordinate, that will also help you in understanding the graphical representation. Okay, Shikhar. So just, I think if you just do the questions from H.C. Verma's two chapters there are. One is first law of thermodynamics and the other is the specific heat capacity of gases. So in H.C. Verma, you will see that after your kinetic theory of gases chapter, there are two chapters devoted to first law of thermodynamics application actually. No, Samar, the adiabatic process graph is different than the isothermal graph. No? The adiabatic process graph, Samar, remember, I'll just take you to the graph we drew above. It is different from the isotherms. Like see in this graph, you can see the red colored graph, that is an adiabatic graph or it's an adiabat. So how it is different from the isotherms, you can understand. No? So that is why an adiabatic compression results in temperature increasing because you're going from a lower isotherm to a higher isotherm. Whereas an adiabatic expansion, that would be opposite to this. This would be an adiabatic expansion. So this would result in the temperature decreasing because A is at a lower isotherm compared to B. So this is what actually helps you visualize the processes in terms of graphs. Is it clear, Samarth? So this will help you in both chemistry and physics. Okay. But particularly in physics, a lot of questions are going to be on the basis of understanding of PV graphs also. You can get a question where the question only is in terms of graph, not in terms of anything else. Let's look at an example. Okay. So what will be given to you in the question itself is a PV graph. You can get that type of a question also. Now this is an example of a question where we will not be able to use the standard formulae because the graph is different than any of the standard processes. So let's understand. So this is again in atmospheres. This is again in liters. Okay. And let's say the particular process given to us, it's a very simple process. It's a straight line graph, but it's not one of the standard horizontal or vertical straight lines. It's like this, let's say. Okay. So, so given that a sample of nitrogen gas undergoes an expansion through a process shown in the graph. Okay. Now, given that pressure at A was 0.5 atmospheres, volume at A was 2 liters, and temperature at A was 200 Kelvin. Pressure at B is 1 atmosphere, and volume at B is 6 liters. Okay. In fact, let's take the temperature lower. We don't want to get into a region of superheating. So first of all, find the temperature at B. Okay. And secondly, find out Q, delta U, and W for the process A to B. Do this much first, then we'll come to another interesting question based on this, which will be related to graph. Yes, very good. That's correct, Samarth. Okay, Durgesh, your answer is correct. Samarth, your answer is correct. And Shikhar, your answer is correct. Anybody else? So see, approaching any question, the first thing you should think about is how we can use equation of state. Okay. So PA upon TA is equal to PB upon TB. So from this you will get the temperature at the point B. Come out to be 600 Kelvin. So this temperature here is 100 Kelvin. This temperature here is 600 Kelvin. This volume here is 2 liters. This volume here is 6 liters. This pressure here is 0.5 atmosphere, and this pressure here is 1 atmosphere. Okay. Now after this, once you got the state, you know the state of the gas at A and the state of the gas at B. So obviously you can calculate for the second part. You can calculate the state function very easily. Delta U is the next easiest thing. It is NF by 2R delta T. So it is, remember, it is nitrogen gas, so it is diatomic. So degrees of freedom will be 5. So it is N into 5 by 2R into TB minus TA. So it is 5 by 2 into this minus this. So state function is the easiest. You don't need to look at the graph. So my state function delta U come out to be 5 by 2 into 6 minus 1 into 10 raised power 2 joules. So the internal energy is increasing by a factor of, how much is this now? 2500 by 2. So that is plus 1250. Yeah, Samarth, your answer was correct. This confirms that. Okay. Now the rest is path function. The next thing we have to do is calculate a path function. Which path function is going to be easy because I know the graph. So area under the graph is going to be easy. No? There's no formula for Q here because it is not some known process. It's some unknown process. Q is 1450. Okay, I'll just confirm that. Okay, all of you are getting different values for work done. So let me just verify. So next thing is, see, we have got the state function. Now, how to get the path function? So in the second part only, work done. That is area under PV graph. Okay. So I need this total area. It's an expansion, so it will be positive of this area. This area. And this is the area of a trapezium. So half of sum of parallel sides into perpendicular distance between them. So that is 4 liter atmosphere. So 1.5 into 2, 3 liter atmosphere or 300 joules. So the work done should be plus 300 joules. Yeah, or more precisely plus 303 joules. Okay. So now we know delta U and we know W. So Q will just come from application of first law. There's no other way to get Q because there's no formula for it here, because it is not one of the standard processes. So Q is becoming 1550 joules according to my calculation. Or more precisely 1553 joules. That's correct. Yeah, Jagannath, I'll take you back to the graph. Yes, Durgesh, that is correct. Formula for delta U is always the same because it's a state function. It is the other two quantities which vary with process to process, Q and W, because they are the path functions. In the formula for delta U, you have to just be careful while substituting the degrees of freedom, whether it is monoatomic gas or diatomic gas. Right? As long as we are dealing with an ideal gas and we are applying kinetic theory of gases, whether the process is standard or not, it does not matter. U का formula वही रहेगा, that it is NF/2 RT. Okay, very good. Okay. So basically, for any non-standard process, for any other process, it is not of the four standard ones. Okay, but as long as the other process is a this thing, uh, quasi-static, that is a slow thermodynamic process. For an ideal gas, what are the equations we can use? PV equal to nRT. Second, Q is equal to delta U plus W. Third, in this, W is integration PdV or area. And fourth is delta U is equal to NF/2 R delta. These are the four standard things applicable to all any process. Yeah. Shikhar, so basically any quasi-static process by definition is reversible. Okay. Irreversible process is not part of our syllabus. Okay. All quasi-static or slow processes are reversible by definition. Okay. Whereas in our physics syllabus, we will not be worrying about irreversible processes. Yeah, so if it is non-quasi-static, then we cannot apply equation of state, because what is happening is while the gas is undergoing a process where it does not have a static equilibrium at every point, So at every point, our equation PV equal to nRT is not valid. The pressure itself within the gas might be variable, the density might be variable. So these equations are then not applicable. The first law general statement is still applicable because it is a statement of conservation of energy in a sense. Okay. It's a work energy kind of relation in a sense. But whatever formula we are applying, like delta U is NF by 2 R delta T, etc., those things, Durgesh, we cannot apply if it is a non-quasi-static process. First of all, we cannot interpret it in that graphical sense only, because at every point, I mean, we cannot interpret the process as if it is going through a curve on the graph where every point is a static point. So then more complex methods like statistical mechanics, etc., are used, which are not within our syllabus, but they are part of physics. Yeah, so at our level now, we have to, like any question that we have to solve numerically using thermodynamics principles, first law of thermodynamics, etc., we have to assume that we are talking about a quasi-static process. Okay, Jagannath, you finished writing this down? Okay. Now let's go through a specific type of family of processes called uh, polytropic processes. So this is not a specific process, rather it is a family of curves. Of the type PV to the power alpha or n or whatever is equal to constant, where alpha is any real number. So polytropic process is any quasi-static process, okay, for an ideal gas such that its equation, okay, on the PV space is of the family PV to the power alpha is constant. So for example, you can see that the special case of alpha equal to 1 is an isothermal process, because PV is equal to constant implies that temperature is constant. Okay. The special case of alpha equal to 0 implies that pressure is constant. So it is an isobaric process. So even our four standard processes are special cases of the general family of curves called the polytropic processes. Okay, now likewise we can see that it is not only isothermal and isobaric, but also if alpha's value is taken as gamma or Cp by Cv, then it becomes an adiabatic process. Okay, and if alpha tends to infinity, okay, then basically Pv to the power alpha is constant. Also implies that P to the power 1 by alpha into V is constant. Okay, so now if alpha tends to infinity, it means V is constant. So this term now gives an isochoric process. Okay, so all the four standard processes are special cases of polytropic processes. Standard four processes are special case of polytropic processes. Okay, but we could have any value. Okay, now for example, if we have alpha equal to minus half, that means PV to the power minus half is constant. That means P is proportional to square root of V. So here the graph of the curve would look like this. This would be some non-standard type of process, but it's polytropic. This is how such a process would look like. You have done polytropic process in chemistry also, no? You're familiar with this from thermodynamics in chemistry? Yeah, okay. So for any general polytropic process, we can use a set of general formulae, which I'm going to write down next. Okay, so let's look at polytropic process. PV to the power alpha is constant. Alpha is any real number. So what we can do here is we can differentiate this. So small change or any change in this quantity is 0. So dp into v to the power alpha plus p into the derivative of this term this should be 0. Okay. So we have the relation, if we take v to the power alpha 1 minus 1 common, we have v dp plus alpha p dv is equal to 0. So that means v dp plus alpha p dv must be equal to 0, or v dp is equal to minus alpha p dv. This is the first thing we understand about any polytropic process. Now secondly, we have the ideal gas equation, PV equal to nRT. So this in differential form is PdV plus VdP is equal to nRdt. So this is our second equation. Okay. So if we substitute this over here, we can see that PdV plus minus alpha PdV is equal to nRdt. So that means PdV is equal to nRdt upon 1 minus alpha. This becomes like our third equation. So first of all, we can see that work done, which is integration PdV, becomes nr delta T upon 1 minus alpha. So this is a formula that we have now for the polytropic process. For any polytropic process, the work done is given by a single formula now. We don't have to do the integration every time. The simple formula for work done is this. Okay. That this equation automatically means that work done is equal to nr delta T upon 1 minus alpha. Or that is the same thing as P2 V2 minus P1 V1 upon 1 minus alpha. Yeah, Jagannath, see the substitution is like this. कि first मैंने इस equation को differential form में लिखा. By differentiating the left hand side, right hand side is a constant, so it's equal to 0. So I got this relation between PdV and VdP. Okay, this product is 0. Now obviously V to the power alpha minus 1 is not 0, so this term only must be 0. So I can substitute VdP as minus alpha PdV in any equation, because VdP plus alpha PdV is 0. So I can substitute VdP as minus alpha PdV. Got it? This. So now you come to your ideal gas equation in differential form. So again, differentiating both sides, I have PdV plus VdP is nRdt. So in this, if I substitute VdP as what? Minus alpha PdV. Okay. So this VdP has been substituted over here as minus alpha PdV. So I'm getting PdV as nRdt upon 1 minus alpha. Okay. Now we know that integration of PdV is nothing but work done. So we can replace PdV as nRdt upon 1 minus alpha, where alpha is a constant. So everything comes outside the integration. Integration of dt is delta T. Okay, okay. Now you understood, na, Jagannath? You substituted the whole term VdP as minus alpha PdV. Substituting VdP as minus alpha PdV. And there's one small little step here, which I've written directly, but we can write down like this. It is nr dt upon 1 minus alpha by integration. So that will become nr delta T upon 1 minus alpha. Okay. And nr delta T which is basically NR into final temperature minus initial temperature, can always be written as P2V2 minus T1V1. So that is why we can also write this in terms of pressure and volume. So therefore, work done, which is NR T2 minus T1 upon 1 minus alpha, can also be written as in terms of pressure and volume. Can always be written like this. Okay, so that is this. Now the next thing is Q is equal to delta U plus W. Okay. Or in differential form, we can write dq is equal to du plus dw. Okay. So du is obviously nf by 2r dt, or you can write that as ncv dt. Okay. Yeah, I'll take you back to the last line. Okay. So okay. Yeah, just a minute, guys. I got disconnected for a moment. Yeah. Yeah. So coming back to this, you know that work done is integration PdV. We have seen that earlier. So differential work done is PdV. Okay. And that PdV is nothing but nr dt divided by 1 minus alpha. So this thing we resubstitute here. So this becomes dq is equal to nf by 2r dt plus nr dt upon 1 minus alpha. So we are once again substituting that same thing. This relation is being substituted. Okay. So from this we can see that dq is n f by 2r plus r upon 1 minus alpha into dt. So we can think of this as a NC dt, where the general term of molar specific heat capacity becomes F by 2R plus R upon 1 minus alpha. Or we can also think of it like CV plus R upon 1 minus alpha. So this is like a universal formula, which is applicable to any of these and any member of the family of curves called the polytropic process. So the two Yeah, so the two important formulae for polytropic process, one is that molar specific heat capacity is given by this formula, F by 2R plus R upon 1 minus alpha, or CV plus R upon 1 minus alpha. Okay. And Q is therefore NC delta T. The other formula is work done is NR delta T upon 1 minus alpha, or P2 V2 minus P1 V1 upon 1 minus alpha. For any process of this type, PV to the power alpha is constant. This is the important couple of formulae. Okay. And you can see the formulae that we've studied earlier are special cases of this. So for isothermal, remember alpha was 1. So what happens here is C is not defined, which we've seen before also. C is not defined for this. Okay. And work done is not defined by this formula because 0 by 0 term we get. Okay. For adiabatic, alpha is equal to gamma. So we will see that C becomes F by 2R plus R upon 1 minus gamma. So when you calculate this now, you will see that this comes out to be 0 because gamma is 1 plus 2 by F. So this will come out to be 0. So C is equal to 0 for adiabatic. And also work done comes out to be NR delta T upon 1 minus gamma, which is basically minus of delta E, which is the case for adiabatic process. For isobaric process, we put alpha is 0. Okay. So you can see that C becomes F by 2R plus R. So that is F by 2 plus 1 into R. So that is CP. Okay. And W becomes NR delta T, which is also the correct formula. Whereas for isophoric, put alpha tending to infinity. So you see C becomes F by 2R or CV, and work done tends to 0. गामा कांस्टेंट बेटा, गामा तो ये होता है ना, इट इज डिफाइंड एज द एडियाबैटिक कांस्टेंट ना, Cp by Cv. This is the adiabatic constant, Shikhar. Okay, and alpha is equal to gamma only na, for the adiabatic process, and also it is 1 plus 2 by f. Okay, so therefore 1 upon gamma minus 1 is actually f by 2. Yeah, if you have a mixture of gases, then we have to calculate gamma by using the concept of internal energy. That the total internal energy of the sample is internal energy of the first gas plus the second gas. But even in that case, for that particular gas, in whatever mole ratio the mixture is, gamma is a fixed quantity. In between a process, gamma is not going to change, not unless the molecules are dissociating or associating or something like that. Is the point clear, beta? So even for a mixture of gases, for a particular thermodynamic process, the value of gamma remains constant unless the molecules dissociate or associate. So that is the important thing. While the process is happening, gamma is remaining constant. 2 by 5 कहाँ लिया बेटा? 2 by f है ना? F is degrees of freedom. Okay. F, this is 2 by f. So maybe the handwriting is not clear. I'll just write it more clearly. This is 2 by f. Okay. That is how this term is becoming f by 2r minus r upon 2 by f. So that is the same thing as 2 by f by 2r. So that's becoming 0. Okay, people. So we'll conclude here today. Next time we will look at some more examples of application of polytropic process and also cyclic process. But then we will focus on moving on towards this thing, heat engines, and eventually, yeah, I'll show you the last time. Heat engines, and then eventually what we call the heat transfer part, conduction and radiation and all that, Newton's law of cooling, etc. So that will be a part which is not common with chemistry. So some extra effort will be required from your part also. Okay. So people, that's it for today's session. Wish you all the best. Okay, people, that's it for today's session then. Next time we'll continue with the same thing. Wish you all the best.